Hello, a very good evening to all. I think in this week, which topics are involved? Dual, primal dual relationships of solution, and also dual simplex method, I guess. Let me share the screen. Is the screen visible to all? Am I audible to you?
Yes, ma'am.
Okay. So welcome you to the course Operations Research. Myself, Jayan Agasri, PMRF research scholar and a particularly teaching assistant to this course from the Department of Mathematics and Statistics, University of Hyderabad. Let's see in this week's content. In this week, we are involved talking about the primal dual relationships and also the dual simplex method. And sensitivity analysis was also involved. You can see the all the sensitivity analysis in the next week. First, see in this week that primal duality relations. Let us see that some notations or some of the basic things which are involved in primal dual relation. Here you can see that weak duality theorem states that okay. So what's the weak duality theorem states? So if we have any asymmetric primal dual problem, and if the primal is greater than or equal, I mean primal is the minimization type, then the objective function of the primal is somewhat greater than or equal to the objective of the dual. That will be stated by the weak duality theorem. uh, and this only involves when the asymmetric primal dual relation only. What is meant by the asymmetric means if any of the primal or the dual problems involved any of the unrestricted in signs, then you can say that would be an asymmetric primal dual case. In that case only, this weak duality theorem can hold. And if we have the symmetric primal dual problem, like in the last statement, optimality criteria theorem, we can say that in a symmetrical primal dual LPP, the corresponding objective function of the primal is equal to the objective function value of the dual at the respective feasible solutions. So symmetric means the solution space of the primal should be equal to the solution space of the dual. Then we can say that primal dual is the symmetric primal dual. And also in that case, we can observe that the objective functional values of both the primal and dual values would be equal. And here there are the another note points that if either of the problems has an unbounded solution, then the other problem has no feasible solution, that means infeasible solution. In clearly you can say that if the primal problem has an unbounded solution, then what about the dual problem? Without solving the dual, can say that if the primal is unbounded, then the dual has infeasible solution, and vice versa. If the dual has an unbounded solution, then you can say easily primal has an infeasible solution. And at the same time, if the primal is feasible and also dual is infeasible, then we can easily say that primal is unbounded. And in the reverse statement also, if dual is feasible and primal is infeasible, then dual must be unbounded. Um, this can be, you can see in the examples in the previous classes. And next we can discuss about the complementary slackness theorem. What is the complementary slackness theorem states that okay, if you have a primal problem, that for the primal we have an objective function of the type maximum of f of x, okay, so that is equal to cx. This is a cost coefficient and decision variable x, and also the decision variable x must be greater than or equal to 0, non-negative restrictions, and subject to the constraints are ax is for the maximization type it should be less than or equal to c, sorry, b would be the RHS, and the you can write that corresponding dual as minimum of, or you can say w of y, another variable is y, then this would be the b transpose y, and a transpose y, that should be greater than or equal to c transpose. Here it is c only, this is cost. So then y greater than or equal to 0. So in this type of primal and dual problems we had, and we suppose that x naught is the feasible solution to primal, and y naught is the same feasible solution to dual. Let us suppose we had these two. Then we can say what the complementary slackness theorem states that y naught uh, y naught into a y naught into a minus c. Here you can say that this is y into a. Why? Because a is a matrix. A transpose, here it is. It will be, if we consider this in this type of also you can consider. So y naught into a minus c into x naught plus y naught into b minus a into x naught. This is equal to 0. So if these are satisfied, then if and only if condition, that means this can also be holds. This can be stated by the complementary slackness theorem. And all, please note all these points that I'll ask you in after this explanation. What would be the complementary slackness theorem? Like an assignment problem. So you can see all this. So previously had seen the complementary slackness theorem, and now we can see that complementary slackness conditions. What are the complementary slackness conditions are? There are four actually, but typically you can say these are in two ways only. First way is if the primal variable is positive, that means after solving the primal LPP, the solution of the primal variable, any of the primal variable is positive, then the corresponding dual constraint will be satisfied as an equation at the dual optimum. That means after solving the dual problem also, at the case of dual optimality, the corresponding, that means let us suppose that to the primal variable positive is the second variable is positive. Then you can say corresponding dual constraint will be, that means the second dual constraint will satisfy a as an equation. That means dual constraint must be greater than or less than or equal to type. But here we are saying that if the primal variable is positive, then the dual corresponding dual constraint satisfied as an equation at the dual optimum. This is the one condition. And in a vice versa, you can say if the dual variable is positive, then the corresponding primal constraint will be satisfied as an equation at the primal optimum solution. These two can be considered as one. That means if primal is positive, primal variable positive, then the corresponding dual constraint holds an equation at the dual optimum. At the same time in reverse. And another conditions are if the primal constraint is strictly inequality at the optimum solution. That means we just had a primal constraint. Let us suppose 2x1 plus 3x2 greater than or equal to 5. But our primal optimum solution is x1, x2 values are 2 and 1. Then after these are the primal optimal solution, let us suppose. So if we substitute these in this given inequality, then we can get 4 plus 3. That is greater than or equal to 5, right? 4 plus 3 is 7. Not only greater than or equal to, but it is following the strict inequality. That means only greater than, not equal to constraint here. So in these type of cases, if the primal constraint is a strictly inequality at the optimum solution, then the corresponding dual variable must be 0 at the optimal solution. So if it is a second constraint which is satisfying the strict inequality at the optimum, then the corresponding variable, that means then the second dual variable must be 0 at the optimal solution. So with the help of these conditions, we can easily say you are going through a correct way or not while solving an LPP. And in the same way, if a primal constraint is a strict inequality at the optimum, then the corresponding dual variable must be 0 at the optimum, at the dual optimum. And next, coming to the primal dual relationship of solution. Suppose we have a problem which is involving in the case of let us suppose that is the primal problem. While solving the primal problem, how can we say that the dual solution without solving the dual? That you can see that if the optimal solution of the primal is let us say x basic variable solutions, it should be b inverse into b. Small b is an RHS, that means the basic variable values, and b inverse is the basis inverse, you know. And the corresponding decision variables xn, letter x is equal to any other decision, any other variables other than the basic or 0. So we are assuming, not assuming, this is the optimal solution of the primal. This is we know. Then how can we say the optimal solution of dual without solving the dual is y is equal to CB into B inverse. We know this CB into B inverse means Lagrangian multipliers or simplex multipliers. So the optimal solution of the dual can be as a simplex multiplier. That CB is the cost coefficients at the optimal level and B inverse basis inverse. So you know, if we know the optimal solution of primal, we can easily find out the optimal solution of the dual without wasting our efforts to solving the dual problem. And okay, optimal solution we are finding, it's okay, good. And what would be the optimal value? I mean, optimal objective value of the dual. Means optimal in a symmetric primal dual case, the objective value of the primal and dual LPP is same, since we had discussed it before. Then the objective value is, objective value of primal and dual both. Dual is, we can say in a notations that CB into B inverse and also LHS value. So this would be the objective value of primal and dual in the symmetric case. And okay, till now we had discussed some theory or some note points involved in the primal dual case. Now we can see here is the problem which is involved in dual simplex method. Why we use this dual simplex method means previously we had solved an LPP by using the simplex method, and if the constraints are greater than or equal to sign, we are solved by using which bigger method or two-phase method, right? And we are also seeing that how to solve with the help of simplex multipliers, that is revised simplex method. So till now we had seen these four types of solving an LPP. Now we can see a dual simplex method of solving. And why we are using this dual simplex method means if any of the LHS, that means the value of the basic variable values are negative, then can use this dual simplex method. Let us see of solving this problem. This problem is involving in minimization type. We can convert this into the for solving we have to convert this into the standard problem, standard LPP. In the first week lecture only I had seen the conversion of LPP into standard. In the standard form, the LPP must be in the maximization type. So maximization z is equal to minus x1, let's say z dash another for the maximization case. Minus 4x1 minus 3x4, right? Then here our constraint are all greater than or equal to sign. In a standard LPP, what would be the constraint? How it would be? Please say anyone here which constraint I have to use.
Ma'am, less than equals to we have to use.
And then
Ma'am,
for
first of all,
we have to multiply the given constraints with a minus sign, then only then we can convert the constraints into less than or equal to sign,
yes, ma'am.
right? Here I am multiplying with minus 1. So these constraints, and after converting these constraints we have to change these constraints inequalities into equations. Here it is the less than or equal to sign, so we have to add or subtract with the slack variable or surplus variable.
Ma'am, add this slack variable. Ma'am.
Okay, then adding a slack variable, that is s1. I am assuming that slack variable is s1, then that is equal to minus 3. Here you can see 2 plus 2x1 plus x2 minus 4x3 minus x4 plus s2 is equal to minus 2, and the objective function would be plus 0 into s1 plus 0 into s2, right? It is the standard form of LPP. Here you can observe that in an initial basic solution, you can say you can observe these are the involved in minus signs of the RHS. So in this case, we use this dual simplex method. First, we write the initial table. You can see here cost coefficient C naught and the basic variables. And here the basic variables are x1, x2, x3, x4, I mean all the variables involved, and also RHS. So the cost coefficients are here -1, -4, -3, sorry, 0, -3, 0 and 0, right? So what are the basic variables here?
S1 and S2, ma'am.
So basic variables are S1 and S2. The corresponding cost coefficients are zeros. And here in this row entries, am I entered in a correct way? The values of the basic variables are -3 and -2. So you can observe these from the given information. And to find out the deviation rows, I am considering that the deviation row would be Zj minus Cj. In a dual simplex method, Zj minus Cj means Cb into Xb minus sum of Cj. Cb into Xb means this C naught into X1, 0 into -1, 0, 0 into 2, 0. 0 minus Cj, minus into -1. So here we had +1. These would be the deviation rows here. I had considered these as a deviation row. So here 4, 0, 3, 0, 0. This would be the entries for deviation row. So in this, after solving these deviation rows, next we have to find out which is the most negative value in the RHS. That means by using the dual simplex method. The living variable criteria is which of the variable has the most negative value, then that would be the living variable. Here you can observe that -3 has the most negative. Here you can say this would be the living variable in this case. So S1 is the living variable. After that, we have for the entering variable, we have to note that just a minute. Okay. So maximum is most or maximum. Most negative row would be the living variable. And entering variable criteria is the maximum of deviation rows. That means Zj minus Cj divided by Xrj. That Xrj would be less than 0. That Xrj are the corresponding constraint coefficients in the living variable row. Here the living variable row is 1, right? This is the living variable row. So in this living variable row, which of the row values are negative that are at the denominator? So if you observe that for the first iteration, the maximum of Zj minus Cj value is for the first. Here we only had a negative values at -1, I mean x1, at x2 and at x4. Is it so? Now we consider the corresponding deviation rows. 1 divided by -1, the corresponding xrj -1, comma, another is 4 divided by -2, and other is 3 divided by -1. Then you can see here it is the maximum of -1, -2 and -3. Out of these, the maximum value is attained at the first case. So I can say that the x1 would be the entering variable in this case. The position only we are choosing, not the value. So this most negative or maximum value is attained at the x1 case. So x1 would be the living variable. Next, the basis is in the basic variable, x1 is the basic and s2. the corresponding cost coefficient minus 1 0, then the corresponding row value should be 1. I mean, we have to change by the row operations. So if we multiply this with a minus 1, you can get the corresponding entry value is 1, and here 3. And also the next corresponding entry column entry should be 0. By using the row operations, I had already done, I showed you 3 minus 2. And you just check it whether this is correct or not. How we can get here 0? In the first case, we had 2. So if we multiply the second iteration, first row with the 2, and subtracting it from the old row, then you can get 0. After getting this, the deviation rows are Zj minus Cj. Here Zj means Cb into Xb minus 1 into 1 plus 1 plus 1 minus into minus plus 1 0. So in a similar way, I had these values. And again, here in RHS, we observe that only one negative value. So it would be the living variable. Only one. There is no choice. And then next, for the entering variable, the criteria would be whatever the variables had the negative signs, all that out of those in the next iteration, out of those we have to find the maximum of those values. That is the deviation rows 2 divided by, here we observe this only minus 3, minus 2 and minus 3, only 3 cases we have. That means x1, x2 or x4 only enters into the basis instead of s2. So 1 by minus 2 and 2 by minus 3. Then we can observe that maximum value is attained at, this means 6.6 or so, minus 0.5 and same minus 6.6. So you can observe that minus 0.5 is the minimum. I mean is the maximum value here in the negative signs in a real line. So this is attained at the x3. The position is x3th position. Second. So in this time x3 would be the entering variable instead of s2. So after solving this iteration, you can next iteration also you can find the solution. And here we can I mean the solution would be whatever the RHS side we have obtained, that would be the RHS. Okay, that's fine. The solution, that's fine. And we see that this is the primal LPP. And with the help of we have already solved it by using the dual simplex. We assumed that given is the primal, then we can say what is the solution of dual. How we can say, previously had discussed it that CB into B inverse would be the solution for the dual case. Here CB in the last iteration, whatever the coefficients we had, that would be the CB, and B inverse means the initially the basic variables are C1 and C2. So just divided it with, so whatever the matrix we had obtained in the basis, that would be the B inverse. Then multiply those, we can get the solution for the dual case. Is there any doubts in dual simplex method? I can tell you when the dual simplex method would fail, and when we can get a optimal infeasible solution. As Aarti,
Yes, ma'am. One doubt, ma'am.
yeah, please.
RHS table all have positive values, ma'am. Then what can I do?
That would be the end of the iteration, end of the dual simplex method. The dual simplex method ends when the
Okay, ma'am.
RHS, all of the RHS values has the positive signs. That is the indication of ending of the this method. Is there any doubts? Other?
But the net evaluation non-negative.
What?
Net evaluations having a negative values now.
Which values? Sorry, I didn't get you.
Zj minus Cj values are a negative mark.
Yeah, I just let you know that at the last iteration, when the Zj minus Cj values, that means deviation rows are negative. Any of the deviation rows are negative. But still the RHS is also in the negative sign, then you can say that is our method is failed. Like in the simplex method, if our method is failed means our minimization, I mean minimum ratio test, if the minimum ratio test fails, then we can say that is an unbounded solution indication, right? So in a similar way, if
Yes,
the
ma'am.
our method, when the dual simplex method fails means the Zj minus Cj values are negative, then you can say our method is failed. That is an indication of unbounded solution. So in a similar way,
Okay, ma'am.
when we can say that this problem has infeasible solution. Infeasible. Anyone had any idea? Then you can say. When the can say dual simplex method is infeasible. Okay, let me tell you. If any of the objective, I mean RHS values or the solution of the basic variable is looking like all are positive. I mean, sorry, any of the value is negative, then the corresponding living variable or the uh, constraint coefficients which are involved in the living variable row that are positive, all are positive, then we can't go through the maximization of like the next criteria for the entering variable criteria, right? If they are nothing negative in the rows, living variable row values. So that would be the indication of infeasible solution.
Okay, ma'am.
Is it understood? Understoodable? When we get the infeasible solution and unbounded. Next questions are involved in the same way. That means unbounded, infeasible, like in the dual simplex method.
Ma'am,
Hmm.
explain unbounded is, ma'am. How to check, ma'am, in dual simplex for unbounded solution.
Unbounded suggestion means here we are considering the row deviations are Zj minus Cj. Here you can observe
Okay.
all are positive. If any of the row deviations are negative, but these RHS values are also negative, then that would be the unbounded solution indication or the method fails.
Okay, ma'am.
Is it okay?
Yes, ma'am.
So infeasible solution also you had understood, right?
Yes, ma'am.
So, okay. Next, go to the next problem. Can I move to the next problem? If you had any doubts in the dual simplex, just let me know. Next problems are also involved in the similar manner. Okay, let me go to the next problem. So here is the question that they had given the question which is assuming it is a primal, and without solving the dual, what is the solution of the dual from the optimal table of the primal? That means they are asking to solve this primal problem, and without solving the dual, just asking about the solution of dual. uh, uh, l- please say that how can we say the dual solution without solving the dual if we had a primal solution? In today's previous lecture, previous talk only had discussed.
Ma'am, CB into B inverse, ma'am.
Okay. So the dual solution would be CB into B inverse when we had a primal optimal table. So first, while solving this problem, first convert the given problem into standard LPP. Uh, for standard LPP, it is in the maximization type, so no need to convert this. Okay, one thing I forgot to tell you in the last problem, just go to last problem. That after solving this, we can get the solution of the primal problem. That is in the maximization type only. Here we had converted minimum into maximum by taking the minus. So the solution would be after taking the minus of the objective value, that would be the solution for minimum case. Don't forget to that. So coming to this problem, and subject to constraints are x1 minus x2. Okay, this is less than or equal to type, and x2 plus x2 x1 plus x2 is greater than or equal to 4. So to convert this into the standard form, that means into less than or equal to type, just multiplying the constraint into minus 1, here x1, x2 less than or equal to 4, and x1 minus 3 x2 less than or equal to 3. These are the subjective constraints, and non-negative restrictions are same, so converting these constraints into equations, 3x1 plus 4x2, you can see, into equations means these are the less than or equal to constraints. We are adding a slack variable. So here it is minus 4. Here it is greater than or equal to sign. We converted it into less than or equal to by multiplying minus 1 on both sides. Here it is minus. So while considering these given information into a initial table, C naught, basic variable, you only has to tell what would be the solution, because it would be simple. While converting into the standard form, 0 into S1 plus 0 into S2 plus 0 into S3. So the cost coefficients would be 0. And here the basic variables are, first you have to find out the basic variables, then only you can go to next. S1, S2, S3 are basic. So the given entries are, so here we observed that the RHS values are, one of the RHS value is involved with minus 4. So we have to solve this problem by using the dual simplex method. So the deviation rows would be Zj minus Cj. Here Zj means Cb into Xv, all is would be 0 minus 3. And next minus 4, 0, 0, 0. Okay. So the leaving variable is corresponding to minus 4, only one minus value is involved. So S2 would be the minus. Before going to the next iteration, if you are looking this table, whether you identified any note on this table, just observe that. I also given you the deviation entries that are Zj minus Cj. Before going to the next iteration, is there any observation point you can find out? Is everyone in call?
Yes, ma'am.
Yes, is there any observation you find here?
I'm not able to find out currently, ma'am.
Okay. Any others? So before just you think it out. I'm reading the comments. Yeah, who raised the hand, please? Higher Aarti asked that if LPP is given in standard form, then its dual pair will be. Yes,
Yes, ma'am.
the conversion of given LPP, if it is in primal, we are assume, then dual would be, if the given LPP is in maximization, then dual would be the minimization type. And the constraints, if the any number of constraints in the primal would be the number of variables in the dual. That all we had discussed in previous class, I think. Here we are, why we are adding slack variable or surplus variable while converting into standard form means so to solve the solution only. But to convert the primal into dual, there is no need to go with this. Three is this optimal initial basic feasible solution? Here we had involved with -4 RHS. And how can you tell? And symmetric or unsymmetric? Who asked this? Aarti? I
Yes,
did not.
ma'am.
I does not get you this question. Symmetric or unsymmetric? What's the? Can you ask in detail? Aarti, you are presenting a screen. Okay, I can clarify with that. The next, coming to, is my screen visible? Are they just stop sharing this presentation?
Okay, ma'am. Doubt, ma'am. If LPP is given standard form, then its primal will be symmetric or unsymmetric.
LPP is only symmetric or unsymmetric? Are you asking that?
No, ma'am. LPP is in a standard form.
Yes.
Then its primal pair will be
Sorry, your voice is breaking. Could you
in
can
a
you repeat?
chat box.
Mhm.
Question will be
Okay, you make your doubt in clear in chat box. Can discuss this now. After finishing this, you can come into that. So here you can observe that the deviation rows are negative values. Before only we are say that for the unbounded solution, if any of the deviation rows are negative, and still the RHS is also involved with the negative values, then you can say that is an indication of unbounded solution, right? Any of the Zj minus Cj, or all of the Zj minus Cj are less than 0, then unbounded. Is it okay? So here we observe that the primal problem has unbounded solution. Then without solving the dual, what we can say about the dual solution? Here this is only the optimal primal problem.
Infeasible.
Yes. So
Infeasible.
Infeasible.
if primal is unbounded, you can say that dual is infeasible. Okay. Next. Okay. Is in this question you had no queries, right? Next, coming to the next question, that for the following primal, it is also in a similar question, that without solving the dual, what is the solution of the dual? Here they are asking same manner. So it is in first convert the given primal into the standard form for solving purpose only, that maximum of z star, that would be the minus x1 minus x2, and subject to the constraints. Here it is greater than or equal to sign, so just minus 2x1 minus x2 less than or equal to minus 8. So converting these into equations, then is this correct, right? And here plus 0 into s1 plus 0 into s2, subject to constraints that are negative restrictions. So and in the same, here we can observe that the RHS values are also involved with the negative signs. So it is better to go with the dual simplex problem. Here C naught and basic variable. We just find out this. If you had any doubts, I can tell you. Why? Because previously I had shown you how to solve with the dual simplex method. X1, X2, S1, S2. Here there are only two variables and two basic variables, so you can easily solve. Not that much time taken. Basic variables are S1, S2, corresponding cost coefficients, and the constraint coefficients. So out of these RHS are negative, which is the most negative value? That would be the criteria for entering variable, right? So here we can observe this 21, the most negative. So that would be the criteria of entering variable. So after that we have to find out which of the row entries corresponding to the living variable are negative, and then find out the deviation row values. The deviation rows means Zj minus Cj, as we see. That means 0, 0 into minus 2, 0 into minus 3, 0, minus Cj, minus into minus 1 plus Cj. So finally you can find out in this way. So after that, the entering variable criteria would be maximum of, again I am showing you why, because for your understanding only, in the dual simplex method. Zj minus Cj given xrj, which value has negative. We may not consider all those, only the negative, whatever the values are negative corresponding row of the living variable, that values only we consider. And that position next for a criteria to entering variable, 1 by minus 3 and 1 by minus 7. So which is the maximum? We can say that 1 by minus 7. So that is for second variable. So x2 would be the entering variable in second case. So here s1 and x2. 0 minus 1 and just solve this. So this is the limit. So that minus 7 would be the 1. How it would be 1? By multiplying with minus 1 and dividing it corresponding row by 7. That means here 3 by 7, 0 and minus 1 by 7. Here minus and minus 7 threes. And it would be 0. When the corresponding column element should be 0, when you can add this row and the old row and the given uh, new row, you can get, if we add only, you can get 0 here. Minus 1 plus 1, 0. So that in the similar way, if we add these two, can get the corresponding entries here. And again, after that, find the deviation rows out of the deviation rows, and here find any of the negative value would happen here or not. Here we are adding this and this, so here it would be minus 5. This would be the only criteria for leaving variable. And find out which is the entering variable. Obviously, it might be x1 would be the entering variable. So x1 and x2 would be the entering variables, and then find out the solution of these primal LPP. Then after solving these to find out the solution of the dual, it would be the CB into B inverse. Here the B inverse is only S1 and S2 are the basic variables. So whatever the matrix here we had getting, that would be the B inverse. Basis matrix only. So CB would be the corresponding cost coefficients. Then you can find out the dual problem solution. And to obtain the objective function value, here you can obtain the solution for x1 and x2. While substituting these x1 and x2 in the maximization problem, we may get in a negative sign, but our problem is in minimization type. So while taking again the minus sign to this maximization problem, we get minimization. So that would be the objective function solution in both of the cases, primal and dual. Nice, is there any doubts? Okay, Aarti, LPP is in standard form. Its primal dual pair will be symmetric or unsymmetric. We are not discussing primal dual pair is symmetric and asymmetric, not unsymmetric. That means whenever any of the primal case or the dual case is involving with the unrestricted insign, you can say it is a asymmetric primal dual problem. Or if the after finding the solution of primal and also the dual, then the solution space of primal is equal to the solution space of dual, then it would be the symmetrical primal dual case. Is it clear? Is that
Okay, ma'am.
you had asked? Is there any other doubts? I just stop sharing this screen and make to present another screen that involves the questions related to these topics only, like assignment, previous year assignment problems. Yeah, the time is almost over. Just quickly respond. We had already discussed that what is the weak duality theorem. What it states that weak duality theorem is for asymmetry primal dual case. In asymmetry means The objective function value of the primal at feasible solution is greater than or equal to the objective function value of the dual. Then what is the answer here?
First option.
Okay. And so here first
Second,
option, second option, F is representing the primal case and W is representing the dual case. The primal is, we are saying that in the weak duality theorem, minimization primal has the more objective function has more than the maximization dual. Is okay? Who said second? Further. So coming to the next question, which of the following is not one of the four complementary slackness conditions? I'll just quickly respond. What are the four complementary slackness conditions? I know there are four complementary slackness. If primal variable optimal solution is positive, any of the variable has positive, then the corresponding dual constraint will
option
be,
D is
it's correct, and this is also correct. When is the strict inequality, then the corresponding variable has 0 at optimal. And if the first and last are same, I mean third. And it's dual of the dual is primal. Yes, it is true statement, but this is not the complementary slackness condition. Is it okay? And if the primal problem is feasible and its objective function value is unbounded, unbounded means that objective function is going to be infinite as the increase in the value of solution. Then you can say that the primal problem is unbounded. Then the dual would be
Infeasible, ma'am.
so infeasible. It's okay. Next, the dual is unbounded. Then the primal is
Infeasible, ma'am.
same. This will be holds for both. One is unbounded and the other is infeasible. And if a primal is feasible and dual is infeasible, then the primal is, we are asking about primal only,
Ma'am, unbounded, ma'am.
unbounded. And in a similar way, you can tell if the dual is feasible and primal is infeasible, then the dual is unbounded. So, and here is the question about complementary slackness theorem. Before that, we had discussed. Just check it. What would be the answer? I am assuming that the first one is correct, I guess. Yes. And coming to these problems, these are only we had discussed in previous. While solving those questions, you can find out the answer of these questions. That these only we had discussed. And if you want to solve, please note the answer. These was also we had discussed in previous table. And finally, this is another question that if a dual constant is strictly inequality, then the corresponding primal variable must be which positive, negative, 0 or none of that. This is also one of the slackness conditions.
Ma'am, zero, ma'am.
So 0, this would be the answer. And this question only had solved in the dual simplex method. The answer would be in this way. Just check, cross check these answers.
Ma'am,
Yeah.
ma'am, one question is from assignment, ma'am.
Which
Uh,
assignment?
and that's provided by the course NPTEL, ma'am.
Okay.
Question was that if the primal has an alternate optimal solution, then dual will have. There are four options.
Alternate optimal solution means they are the multiple solutions, right?
If the primal has multiple solutions, then what we can say about the dual, ma'am? dual
Uh,
solution.
yes, you can check it. I may not say the answer because that are your assignment problems. We don't have to tell or reveal those questions. But you just recheck with the previous lectures. If you not find, then in the next week I can tell you.
Okay, ma'am. Okay.
Yeah. And any other questions or doubts, queries? Please welcome.
Ma'am, in dual simplex method, ma'am,
Mm-hmm.
ma'am, for infeasibility, ma'am, that leaving row, all
Mm-hmm.
the entries must be positive, ma'am.
Yes.
That's the only sufficient condition for infeasibility in dual simplex method, no, ma'am?
Yes, but we observed that the RHS is negative, but the
Huh.
corresponding row values are not negative.
All are positive, ma'am.
Yeah, all are positive. So,
Okay.
any other queries? Okay, anyone please tell that what are the topics involved in next week? Whether you observed, I mean, you are entering into this week, right? This week, week 5, what are the contents in week 5?
Ma'am, sensitivity analysis, ma'am.
Huh?
And ma'am, there are two case study exercises, ma'am, and then integer programming, ma'am,
Okay,
and then goal programming, ma'am.
okay. Is that all
Yes, ma'am.
only? Integer
Yes,
programming,
ma'am.
goal programming, and sensitivity analysis. Okay, fine.
Yes, ma'am.
So we can discuss all those in next week. I just stopping share. So if you had any
Thank you, ma'am.
other doubts up to now, you can write anywhere and ask me in the next week. I can any queries are welcome. Okay, just terminating this call. Thank you.